Now let us have a look at how Cortex-M4 executes code. Now we know that most of the instructions of Cortex-M4 are 2 bytes. That is, they follow the thumb2 instruction set. So whatever you see, this is actually a memory area. I have depicted the opcode. So whatever you see here are the opcodes. Opcodes are the actual machine codes. So if you have an assembly, the assembly code is a human understandable form, but the opcode is the machine form. So say if you have push R7LR. So this is something that I'm picking out from actual code. The opcode for that is B580. That is the operation code. So push R7LR does not go into the machine. What gets written into the flash is this, and this is the lower memory. So 80 is written because it's little endian. 80 is written first and then B5 is written. So 8000198 has 80 and 199 has B5, and then it goes on from there. 19A has 82 and then B0. So this is one instruction. This is one instruction. This is another instruction. This is another instruction. So these are opcodes basically. Now the program counter job is actually to fetch these instructions, and since we have a 32-bit bus on the Cortex, so since this is 32-bit, the fetch happens for 2 instructions at a time. So one instruction, and because 2 instructions make 4 bytes, so 2 instructions will go into the processor in one time. So this is the instructions get processed in this sequence. First it's a fetch, then it's a decode, and then it's the execute of that particular instruction, and then it goes again into the fetch cycle. So this keeps happening. So the PC, so in our case, this could be, so the address actually starts from 8000000. Now why the code did not start from there is again another topic of discussion, because we will have something called as the exception vector table in the beginning of the flash, and they say this is from where the actual code starts, and then we will have a look at the exception vector table and the memory layout in more detail in the later sections. So this is from where the opcode start, and the PC is incremented by 4 bytes. So from here, so when the PC is here, say the PC is here, it will actually take in 2 opcodes, and the next jump of the PC is going to be here. Next PC increment is going to be here, so it increments by 4 bytes. So that is how the PC operates. Even though the instructions are 16 bits, it jumps at 32-bit boundaries and then grabs the instructions. So if there is a 32-bit instruction, then if the PC jumps 2 bytes, then it will be only one instruction that is coming in. But if it is 16-bit instructions, when the PC jumps for 4 bytes, it gets 2 instructions. Now, so this is how it operates. Now, if you really want to know more about what opcodes correspond to what assembly, then you can refer to this document, that is the ARM7M architecture reference manual, in case you're interested. Okay, so if you are interested in to look at what is the mapping between opcode and assembly, look at this chapter A5, which talks about thumb instruction set encoding, and it gives you how different instructions are encoded, how move or any instruction encoding happens. So this is how So you have bit 10 to 15 as the opcode, and then you have the other options here, so on and so forth. So you can take a look. It will give you an interesting insight into how the opcode works, how the controller knows whether it's a 16-bit instruction or whether it's a 32-bit instruction, so on and so forth. It's quite interesting actually. Now this is the diagram of the three-stage pipeline that we have been talking about so far. Now say this is the clock that we are this is the main processor clock, and we have, so pipelining allows hardware resources to be fully utilized, and one 32-bit instruction or two 16-bit instructions can be fetched. Now what do we mean by a pipeline? A pipeline means that in one clock cycle we can do multiple tasks. So when the processor starts executing, it fetches the first instruction. So this is considering the instructions are 32-bit, not 16-bit. So it fetches the first instruction in the first clock cycle. It has got nothing else to do there because it does not have anything in the pipeline at that point. Then in the second clock cycle, this instruction that it has fetched, it starts decoding that instruction. Okay, but in the second clock cycle also it can fetch the next instruction. So it is doing two things in this clock cycle. It is decoding the first instruction it fetched, and it is picking out the second instruction. So instruction I means this goes on for any instruction number. If this was instruction 10, then it is instruction 11, 12. So it goes on like this. So when I mention first instruction, it doesn't necessarily mean the first instruction. It can be a snapshot of any instruction fetch in the controller. Second instruction fetch. So here, consider this as the pipeline. So this pipeline, this is the only, it's a single pipeline, but this is moving in time. So the pipeline is moving in time. It's only one pipeline. So this pipeline has only the task of decode and fetch. Now when it moves to the third clock cycle, this instruction that it has decoded, it can execute. But at that point, this instruction that it has fetched can be decoded. And while it is executing the first instruction fetched, decoding the second instruction it fetched, it can fetch the third instruction. So this is where the beauty of a three-stage pipeline becomes clear, where in one clock cycle, one instruction is executed, another instruction is decoded, another instruction is fetched. See in the next clock cycle again, when a next instruction fetch comes, if you check this pipeline, so when the pipeline is, at this point in time, again you have instruction execute, decode, fetch. Three things are happening together. Again, another instruction, if it comes in, it will be 3. If it stops here, then it will taper off. 3, 2, 1 and done, because there are no more instructions coming after this. But generally, when the instructions keep flowing in, this is how your pipeline works. 3 activities in one clock cycle. The clock is fast. On top of that, there's a pipeline, so you can imagine how fast the execution is going to be. Now, this is for 32-bit instructions. Now, what happens when you have 16-bit instructions? So this is how the diagram looks when you have 16-bit instructions. For example, now you have a instruction fetch which is 16-bit. 2 16-bit instructions are fetched this way. First instruction and second instruction in the first clock cycle. But there is nothing else to do here. Say if it's the first instruction that it fetches, or we are just looking at a time slice here. Second clock, the first instruction that is fetched is decoded. Okay. And the next 2 instructions are fetched here. So the first instruction is decoded. The second instruction is not decoded here, but the next 2 instructions are fetched. Then in the third clock cycle, that first fetched instruction is executed. Then the second instruction that was fetched is decoded at this cycle. Then again in the fourth clock cycle, the second clock instruction is executed, and these 2 instructions that are fetched, one is decoded. And in the next clock cycle, this instruction is executed, and in the next, this one is executed. So there are four instructions that are executed in 1, 2, 3, 4, 5, and 6 clock cycles. So this is how this works. Okay, so for a 16-bit fetch, the pipeline looks like this. Here are certain places where you will get a hint of the pipeline execution. So we will come to this piece of code later when we are talking about linkers and makefiles. Nevertheless, I've just brought this code up ahead in this chapter because I needed to explain something. So now this is the C instruction that we would be issuing, and when we look at the disassembly, these are the assembly instructions that the assembler would have generated for you. So now when you look at the disassembly, this is a load instruction, and it loads some value from a PC offset, that is offset of 152. Now this is something that needs a little bit of explanation, because it is not as straightforward as it looks, and this hints to a pipeline that is working in the in the backend. So for example, so what generally happens is, if the opcodes is not able to accommodate a large number like this, that is, you do a load some value into the R3 register, okay, and that value happens to be a 32-bit value, then the opcode cannot accommodate for that value. So what the assembler does is, it conveniently puts the value in the flash itself at some offset from the program counter. So if this is the line that the controller is executing, then this will be at an offset to that particular program counter. So offset to a program counter would mean that even when this code is relocated, we'll talk about relocation and things like that later. So even when this code is relocated, this difference between the PC and the value that we have here, so this is a value, this particular offset is constant. If you move this to some other location, PC moves along with the value, keeping this offset constant. So now here let us do a little bit of calculation. So we have LDR R3 program counter with an offset of 152 decimal, and that points to memory location 8000304, and 8000304 memory location is here, this one. Now let us open up the calculator and add 152 to this number, that is 8000268. So let's add 152 to that. So let's see what 152 is in hex first. So let's see that. So 152 in, so let's see, 152. So in hex it is 98. Okay, so let's note down that number here somewhere. So in hex it is 0x98. Now let's switch back to hexadecimal here. Let's add this value 80026A to 98 in hex. Okay, 152 is, since 152 is 98, so 80002 to 6A, and then let's add 98 to it, 98 hex I mean, and the value that you get is 800302. Can you see that? The value that we have got is 800302. Okay, now that is not this address location. So when you add an offset to this particular memory location, it should have been 800304. But that is not the memory. It is pointing to somewhere in the middle here. So this might confuse you when you actually look at disassembly. Now, what is generally happening here is this is because of the pipeline. So by the time this instruction is decoded and executed, this particular instruction, that time the PC value would have changed. That is, the program counter value would have changed, because it's a pipeline. So whenever it's a pipeline execution, whatever instruction is being decoded and executed, during the decode and execute, the PC would have moved ahead. So during the decode and execute, the PC would have moved ahead and started fetching the next instruction. So naturally, when the actual decode and execute is happening, the PC value has changed and moved ahead, which is why the offset is lesser. Okay, so in this case, say the PC has moved ahead by 2 bytes. So it is PC plus 152, but the PC is not 8026A anymore. It is 8026C. So when this is decoding, it is offsetting on the value of 8026C and not 8026A. And that is the reason why you see there is a difference in this. And generally there is a formula which talks about offset plus 4 bytes. Okay, so this would have been, but we see that this is a difference of 2 bytes. Okay, it's 00302 and we see it at 8000304. So this is 2 bytes. Now that happens because to this address location, so whatever is this address location is, so 26A. So when you have 26A, the assembler adds 4 to 26A first. Okay, so let's go to the calculator again. So assembler adds 4 to 26A. So let's drop this out so that it's clearer. So let's say this is 26A plus 4. So we have 26E. Now E, so whenever you get some value like this value is not word aligned. It is half word aligned. Can you see this? It's 10. Okay, 10 is half word aligned. So by default, what it does is it changes this to a 0. So it changes this to a 0. When it changes this to a 0, that is the reason. If it were word aligned, it would leave it like that. So it will try a 4 word aligned, and if it were aligned, plus, if it would do a +4 and it sees that it's word aligned, so this value 80026A, and it would do +4. It would do a +4 and it would say that the resultant value is word aligned. It will use that address here. Okay, if it is not word aligned, then it is going to make it word aligned, and then it will use that. It will put the particular value, whatever you are trying to store, in that particular address. So that is the reason whenever you see that it is not matching up with the offset, this is what is going on in the background. So this is something that you need to be careful about, and this is because of the pipelined execution. And moreover, you don't need to worry about this, because first of all, we are coding in C. Even if you were coding in assembly, you would still not have to worry about the offsetting, because you just put the absolute value, and the assembler will take care of assembling. Creating the opcode accordingly. Okay, but this is something that you need to know. Now let's have a look at the different processor or controller variants that are available from ST on the STM32F4 series. So this is the website. Let us go to their web page, check out their controllers. We have STM32F4 series of high performance microcontroller unit with DSP and FPU instructions. Okay. So the ARM Cortex M4 based STM32F4 MCU series leverages STM's NVM technology and ART accelerator to reach the industry's highest benchmark score. So it writes about the controllers, and it talks about with dynamic power scaling, the current consumption running from flash ranges from 89 microamp per megahertz to STM32F410, which is about 260 microamp per megahertz on the STM32F439 and so on. So it talks about the power consumption and so on. Let us look at the different lines of controllers that are available. One is the advanced line, which is 180 megahertz, okay, CPU with a 225 DMIPS and up to 2 megabytes of dual bank flash memory with DRAM and CROM ART accelerator. Okay, so these are high-end microcontrollers. It has got a quad SPI interface, LCD TFT controller, MPI DSI interface, and so on. This has got serial audio interface, more performance and lower static power consumption. So this is the advanced processor line. Then you have the foundation line, which is STM32F446. This has got a frequency of 180 megahertz, 225 DMIPS, and up to 512 KB of flash memory with dual quad SPI SDRAM interfaces. STM32F407417 is a very popular discovery board, which falls in the foundation line again. It has got 1 megabyte of flash memory, adding Ethernet MAC and camera interface. Then you have STM32F405415, which is 168 megahertz CPU with 210 DMIPS, 1 megabyte of flash memory with advanced connectivity and encryption. We are using access line controllers, which are basic entry-level microcontrollers, but they're powerful enough. So these are 84 megahertz, 105 DMIPS, smallest cost-effective solution with outstanding power efficiency, called dynamic efficiency. So STM32F401, it's got less than 3 millimeter by 3 millimeter die size with USB 2.0. We are using STM32F411 here. Okay, so 410 has a new outstanding power efficiency. This one has high RAM density and enhanced peripheral set, like USB 2.0 is there with 5 SPI interfaces. Then you have STM32F412, high RAM and flash memory density USB interface. You have 412 has CAN and quad SPI dual mode, everything. STM32F413 again extends the STM32F412 features for higher RAM and flash. So you can see the variety of controllers that any vendor makes. So if you are using a different set of microcontrollers, then you have to go to that particular vendor website and check what they're supplying. So you have a wide range to choose from, and that also increases your chances of mistakes. You have to be very careful about choosing the controller suited for your needs, which will meet your technical requirements and your cost constraints. So this is whatever we saw here is put in a tabular format, whatever all the controllers that we saw till now. So you can have a look, you can go through this web page, and the address is st.com/en microcontrollers microprocessors /STM32F4 series HTML. I'll try to put this link in the course material so that you can access this web page. But anyway, you can see the link on top in case you want to have a look at it now. And then STM32 has an ecosystem where we'll be using this IDE. It's a free IDE, STM32Cube. We are going to use the STM32Cube IDE. We are going to use STM32 Flasher, that is to flash our code on the board. And you can have a look at all of these sections in the ecosystem. It has got a solutions. It also provides various solutions for various artificial neural networks and audio, voice, and connectivity, graphical user interface, motor control, safety, so on and so forth. Okay, so and say you go into motor control again, and it'll provide you with solutions on motor control and processors that it supports. For example, how much flash you have, and then how performance-wise, what are the different how the different microcontroller families fit into this particular motor control ecosystem, so on and so forth. Okay. So it makes sense. You can have a look. This is the controller we are working on. This is the access line controller that we have, and we are using a discovery board with this controller on it.